Okay, back to class. For schedule, again, Monday's recitation with the video was on debugging, which you're going to need after this week. And today we make electronics. And once again, this was a flip. Sorry, excuse me for a minute. This is a flip. In the past, we had you make electronics, then design, then program. Now you've programmed, designed, and you're going to make. So the group assignment is going to be characterizing the PCB production process. Individual assignment is you're going to make and test the board that you designed 2 weeks ago. So we need to go through types of PCBs, processes to make them, and how you assemble the components. So you're no doubt familiar, a printed circuit board is a board holding components. A standard way to do it is by etching. And we're not going to do that. Claire's glad. I'm glad to hear from Claire that the car is okay on the bridge. Thank you, Claire. So etching chemically removes material. And this is how it's done commercially. You spread a photosensitive material. You expose an image, develop it, and then you use chemicals to eat away the material. There are other ways you can do it. You can do it with toner transfer as a printing process. And you can do it with printing directly on a board. And this shows an example of that. Excuse me. The standard materials for that, ferric or copper chlorides, are really nasty chemicals. So this is commonly done, but it produces hazardous waste. And a good guide to that is, this is an article on the water consumption. And for a 1 meter square board, you consume about 1 meter cube of water that becomes chemical waste. And then that's very hazardous waste, and disposal, it's a real disservice. If you do it at home or in the lab, if you pour it down the sink, it etches the plumbing and pollutes the watershed. So there are friendlier materials. This was a project from Kamakura using what's closer to kitchen chemistry, of using etchants that aren't as toxic. And so we're going to be talking at a few times about safety data sheets, SDS, which are references for chemicals. And so if we look for ferric chloride and you view the SDS, these explain all of the hazards. It's very hazardous to ingest. It can cause eye damage. It can corrode skin. And so for all of those reasons, what's good about chemical etching is the feature size. You can make very high resolution traces. And the other thing that's good about it is it's a batch process. So if you have a large board, if you have many boards, they all get etched at the same time. What's bad about it is there's a setup. It's not direct, what's called direct write. You have to transfer the image to etch it. and then you need to dispose of it very carefully. Yeah, Jason is noting also experimenting with using resin printers for PCB. Let's see. Let's see. I'll mention there's a note about the Volterra. I'll talk about that in a little bit. So if I do etching in my lab at MIT, there's a whole department involved in making sure I safely dispose of the chemical waste. So against that background, the main process we're going to use is machining. This was a series of videos from a student in the era of Google Glass, where if we get to the essential one, we're going to use a tabletop milling machine, and you'll send the design to it, and the machine will mechanically remove the material. The reason we like this process is it's not the highest resolution process, although it can be surprisingly good. It's not the fastest process. It's not a parallel process, but it is direct write, meaning you just send the job to it and it starts making it. There's nothing to set up. And what you can see in this image is what's left. The waste is just a little bit of dust from the machining to vacuum up. And so it's completely not hazardous. There's no reagents, there's no disposal, and every job can be different, are all the reasons we like machining. And so in your lab is some form of a precision milling machine. And over the years, we've used tools like these roll-in machines. There's a number of other ones, but it has to be a good one that these are specified below 1/1000th of an inch tolerance, which we need for the resolution of the machining. And then in large format machining, you saw a range of tools. For this week, it's a much smaller set that we'll be using. So this is a workhorse tool. It's a 1/64th inch end mill. Loading slowly, but these cost maybe $15 each, and it'll last through tens of boards. So making one board consumes tens of cents from the life of it. This is a smaller end mill, 0.010 of an inch. It's much more delicate, and it takes a longer time to machine an area. So we only use these for the tiniest features. And this is a somewhat larger tool that's somewhat longer, and we use that to make cutouts in the board and to cut the outline of the board. Arnie's asking about FR2 and a milling smell. Boy, I'm not familiar with smell from machining. That's usually a sign of overheating, unless there's some odd resin in the FR2. Like, are the chips discolored from it?
No, there is no high heat involved. There's no discoloring. There's just a slight smell. It's nothing horrible, but it's a distinct smell. Nonetheless, maybe it's just sensitive noses.
Yeah, right. I think that's all it is. So I'll shortly talk about materials. FR4 is hazardous to both you and the machine. MDF with bad resins can outgas hazardous materials. I'm not familiar with FR2 doing anything hazardous. Ricardo's also noting, again, I'd be a little suspicious about something getting too hot. something's getting hot somewhere, of a motor heating or a tool heating. Because yeah, I'm just not familiar with the smell from it. So in any case, we use these end mills to cut traces. You can get V-bits. These are much cheaper. What's tricky about the V-bits is for the end mills, when you're machining, the depth doesn't matter. It always makes the same trace. For the V-bits, what they do is the width of the cut is a function of the depth. So you can make slim traces with them, but they're very sensitive to the height. And if the height changes at all, the width changes. And the other thing is you can't use the V-bits to make multiple clean passes like you can with the end mills. So the V-bits are cheaper and they can make a clean isolation around a trace. They're less good for machining. Chris is noting the V-bits are more robust. They're much harder to break and they are cheaper. So those are all reasons for V-bits. Now, for what we're going to do, there's the board we're going to make. It's on a sacrificial layer because we need to cut into something. That goes on the machine. Then the end mill goes into a tool holder that goes into a spindle. Then all of this is connected to the machine that moves the bed. And the distance between the tool and your stock is very sensitive. We're only going to mill a few thousandths of an inch down. And so this is called a force loop. And it's critical that all of this doesn't introduce any more tolerance than that. So there are a number of things that go into that. So first is holding the stock down. The most common way we do it is we use it just with double stick tape. And that may seem crude, but you can either use double stick tape, or something I like to use is, let's go to the inventory. And let's see, in the cutting week inventory for the vinyl cutter, this material, this is an adhesive on a backing that's easily removed. And so you can use this to transfer adhesive onto your board to hold it down. Michael's asking about what happens to the tool lifetime. So when the tool is, let's see, come up here. When the tool is brand new, the flutes are very sharp. And when you mill, you get little bits of sort of fine hair on the traces that are easy to get rid of. As you mill, it gets very slightly rounded, and that actually gives you a cleaner cut. And then late in life, the tool gets dull, and then it's sort of smushing it, and you get a really rough cut. You can do that surprisingly far. When you get what looks like a rough cut, from the side, you have your trace, and then there's a little bit of sort of crud at the end of the trace from the machining. You can then deburr. And one way to deburr to get rid of that is to use a fine abrasive. The way I tend to do it is, this is just a steel rule with a sharp edge. And if you just drag that across, you can also deburr. But when you start getting not fine features, but sort of rough features, that's when the tool is getting old and needs to be replaced. So for fixturing, the most common way we do it is just with tape underneath, because the machining forces aren't particularly large. Now, another way you can do it is, if this is the board, is to just mechanically clamp it. But the issue with mechanically clamping it is it can bow the board just a little bit. And that does two things. One is, I'm exaggerating, but when you bow the board, the height varies. So for example, for a V-bit, the traces isn't uniform. But the other thing is there's stress in the board that can put force on the tool and can lead to breaking the tool. So clamping the board works as long as you have nice clamps that distribute the force, and the board lays flat after you clamp it. It doesn't work if you get a little bit of bowing in the board. So you hold the board down. Now, one of the most common problems in Fab Labs machining boards is, here's our board, there's the underlay, you mill into it. And if I look from above, every machining job leaves a cutout in the underlay. And when there's enough of them, the underlay surface itself is so rough that it doesn't hold your board down well. So the underlay is sacrificial and you need to replace it. And generally, those don't get replaced often enough. And if the underlay needs to be replaced and you didn't replace it and you put your board down, what's going to happen is, as you machine, your board is going to move around a little bit and you'll get sloppy results. So the underlay has a lifetime that you need to replace. Then comes, here's our collet holding our end mill. Here's the PCB we're going to mill. We need to set 0 right here. So one way to do it is, there's a set screw typically that holds this. You can loosen the set screw and then gently lower the tool down. You don't want to drop the tool because you can break it. Gently lower it down. That's a little more subtle than you think, in that if there's a little bit of machining chips on the tip of the tool, it means the 0 is off. And when you tighten the set screw, the tool can move a little. And so what you want to do is actually kind of tap the tool to make sure it's making good contact, and then hold the tool with one hand while you tighten the set screw with the other. Another way, a different way to do it is to, that I don't recommend as much, but if it's hard to change the tool, to change the tool with the set screw, is to just like manually spin the tool, or gently spin the tool as you lower it. You can, for example, have a piece of paper and you move the paper back and forth as the tool comes down, and you stop when the paper can't move. So how you do that will depend on your machine, but you need to set the 0 very accurately. Then the tool is held with a set screw, and a common beginner mistake is to significantly over tighten this. You're not cranking it down, it's just snug. You don't need much torque. And the problem is, the set screw has very fine threads. And if you over torque it, you're smushing the threads. Eventually you strip the tool holder and you need to replace it. So it's snug, not more than this. So we mentioned the tool has a lifetime, typically say tens of boards. When it's done, you want to get rid of the machining burrs. Then the next thing you want to do is clean the board. There are oils from your finger, and you can't see it right away, but over time, they'll tarnish the board. They'll start actually eating away at the board. So before you solder components, which we call stuffing, take the board out and just wash it in soap and water, make it clean. And then something also to be aware of is, remember from last week, climb machining is where you turn that way, going in this direction. Conventional machining is where you go in that direction. Um, uh, Conventional machining is better for heavy duty machining. Climb machining gives you a better finish. Typically, this is better for what we're doing for machining. It's very fine feature sizes. So typically we do it in the climb machining direction. Okay, so those are all the steps to get set up for machining. And that's the main process we'll be using this week. Then there are a few other optional processes. So the vinyl cutter, some people fall in love with it and use it to do their machining. So this was an example of using the vinyl cutter to make 3D circuits. And Hong Hao has some nice videos. So there's a lot going on in this example. You're pushing the resolution of the vinyl cutter. So the first thing he's going to do is he's taken the copper and he's removing it from its backing. So the copper has a backing, but it doesn't adhere very well. And so he's removing the copper from its backing and he's putting it on another material. This is the epoxy film we use. Then you see that flexible plastic substrate. He's putting that underneath. And what that's doing is it's stiffening everything. If you don't do that, the vinyl cutter knife pushes on the copper and it smushes it. This helps keep everything in place. So then he does the cutting, and that's very fast. That's just a few minutes. Now he's doing the weeding. And if you cut too deep, it's a shredded mess. If you cut too shallow, you can't weed it. But if it's just right, it comes off beautifully. And in particular, the main lesson in weeding, let's see where he gets to the weeding, is you don't lift, you shear. You pull in plane, and if you did everything right, it just beautifully comes off. And then when you're done, there's two great things about this. So it just beautifully comes off. When you're done, what's nice is you can lay up multiple layers. The whole thing is flexible. It can be large. And so you can make beautiful circuits that way. Then you can use it to make connections. This was a project where he used the vinyl cutter to make traces that he put on cardboard tiles to make circuits. And you can encapsulate. So Victoria fell in love with the vinyl cutter. When you're done, the traces aren't anchored very well. And so as a final step, what she does is she just paints or dips everything in acrylic to seal it, to make it more robust. And then a funny hybrid is, this was a student doing something that never occurred to me. Rather than buying PCB stock, she laid up, she made her own board with the copper we use for vinyl cutting, but then she milled it on a milling machine to make her own boards on substrates as a hybrid. So all of that is a process. I wouldn't start with it, but that's an option. Then a CO2 laser doesn't remove copper, but a fiber laser, which is a shorter wavelength, about 1 micron, does. And so, yeah, here's another example of a broken link, which is why I like these in the repo. And so if you have a fiber laser, you can use that to remove copper. And that's a nice process. The issue is the fiber lasers cost tens of thousands of dollars. They're much more expensive, but you can make really nice boards that way. The issue with copper is you get very fine hairs. And so you either want to defocus the laser or make passes in both directions. Jason is noting painting and using a CO2 laser. Jason, I've never seen that well. Have you? I've never seen that work for the kind of resolution we're doing. I'd be interested if somebody could report on that. So that's lasers. Then there are a number of kinds of printing processes. So this was using inkjet printing silver ink to make circuits is one process. And then the resin print mask. This is a company spun off from a colleague that has a head that dispenses conducting material and plots circuit boards. In theory, that works great. In practice, it has a couple issues. It can be somewhat fussy for the deposition process, and the plotted traces typically don't match the performance of just milled copper. And so in theory, you just plot out the board and you don't have to do any of this. In practice, it's hard to match the performance of what you're going to do from just milling copper. So that's a printing. And then you should be aware that in large volume, when, for example, shoplifting tags with little circuits are made by the mile, that's done by plating. That's where you print a poor conductor and then you put it in a bath and you grow a good conductor on the poor conductor. And that's a fairly friendly process. You can do that in the lab. And finally, you can sew with conducting threads. This was a very early paper on that from my lab, where you have an embroidery machine, but you do it with conducting threads. This doesn't make very fine, high conductivity circuits, but for things like interactivity in clothing, you can use conducting threads. So machining is the starting focus, and then these are all other options you can experiment with. Now, for PCB materials, FR4 is the most common one. It's typically greenish, and you don't want to let this near the milling machine. The issue with, let's see, let me make a note. The issue with FR4 is it's glass reinforced epoxy, and it's bad for you and it's bad for the machine. It's bad for you because the glass can't deform elastically, and so it ends up killing the tool. The tool dies quickly. And then the other issue with FR4 is, we'll see this in composites, when you machine it, what I described as harmless dust for FR4 is short glass fibers. And this is exactly what makes asbestos so dangerous. And this is why miners get lung disease. This is hazardous waste that you don't want to breathe and you need to dispose of carefully. And so for those reasons, you never ever machine FR4. You can put it in the machine and it'll mill, but you're killing your tool and it's hazardous for you to be around. So we etch FR4, we don't machine it. What we like to use is FR1 is a fiber reinforced resin. We order it from this company in batches, and you can get it through resellers. FR1 is typically brownish, not greenish. And so it's a phenolic, typically something like paper or fiber reinforcement. This machines beautifully easily and is completely not hazardous. And so that's what we use for the machining process. You can buy sheets of the underlay, garolite, and you can lay up copper on it. And so if you get excited, you can actually make your own. But that's what we use for machining. For flexible circuits, commercially, it's done with Kapton as a material. That's a fairly expensive process. But with the vinyl cutter, the backing material we can use is an epoxy film that looks like vinyl, but it's much stronger and handles higher temperatures for soldering. And then we use conducting tape. The tape has an electrically conducting glue. It's not a great conductor, but it's a good copper that you can then solder to. And with that, you can make flexible circuits. If you go to still higher frequencies, boards are made out of Teflon. Glass actually makes a good radio substrate if you get to very high frequency circuits. Now, a funny number is the copper is measured in ounces. And that's the most common way. So you'll hear about 1/2 or 1 or 2 ounce copper. That's referring to the weight of the copper, but this corresponds to the thickness. And you'll see it's just tens of microns of copper is what we're removing. And so that's why the tool needs, the tool cut is very shallow. It just needs to get through that thickness. So that's making boards. Commercially, the board stock is made by heating and squishing. You take copper foil, you take I've got it linked here. You take an adhesive sheet and you take the board and you heat and squish. That's how you make the boards. And then commercial board houses, which I'll talk about now, uniformly do it by etching. So they'll take your board with many other people's boards, put them on big panels, make a mask, expose it, and etch it. Now, the good news is, thanks to so OSH Park is one board house that's very maker friendly in the US, and two that I make a lot of use of in Shenzhen. One is JLC PCB, one is PCBWay. These are comically cheap almost. The cost here has come way, way, way down. So let's say we had a 10 by 10 millimeter board and we want 10 of them. It's going to cost $5 to make it. The main cost is just shipping, but even then it's $25 to the US. Now, their cost, because this is a batch process, isn't sensitive. So if I go up to 50 instead of 5, the price is still $5. And so it's a few day turnaround and then a few day shipping. And so if you're not near Shenzhen, it takes about a week round trip. And of these two, JLC PCB is really convenient to use, friendly interface. PCBWay, you need to know a little bit more to use it. It's a little more complex, but they can handle standard, many more processes. So they can do flex, they can do all kinds of variants of thin boards. This shows you the feature sizes. A key parameter is how skinny can a trace be and how close can traces be together. This is a standard, but you can quote pushing below that. And typically, let's see if that goes up. Typically, that'll raise the price. Yeah, so I went from 6.6 to 3.3, and it went from $5 to $120. But the standard processes are really cheap and convenient. So I don't use this to make one board. While I'm developing, between 1 and 10 boards I make in-house. Once I get up to wanting about 10 boards, I then send them out to board houses. This is an amusing company. They make not just, they make all of the tools you need to make PCBs in production. And then these board houses, in addition to making the board, they can, you can send them a kit of parts and they'll do the assembly, or you can give them a bill of materials, and assuming the parts are available in inventories, they can actually take your bill of, BOM is bill of materials. They'll take your bill of materials and they'll actually give you the board assembled. So those are board houses, and in-house, 15, maybe 10 thousandths of an inch is what we use for the traces. The board houses go down to around 5 thousandths of an inch before it gets much more expensive. Then when you send a job to a board house, there's multiple layers. there's the traces, mechanical is the outline, drill is whether there are holes in the board, solder mask is on the board, there's, let's say this is a pad, there's a mask above it that isolates. So solder just goes where it's exposed, but the rest of the board is masked. And then silkscreen is a text layer that lets you put word and text on it. We don't need that in-house if you're just milling copper, but you need that when you send it to a board house. Now, a key thing for this week is layers. This is a 1-layer board. Everything fits on one side. So that's quick and easy to make. This is what you could call a 1.5 board, because you'll see right here, I needed to get this wire over to there. And so what I'm doing is I'm using a 0 ohm resistor as a jumper. I could solder a wire, but it's faster to make pads and just put in a 0 ohm resistor. So I use that to hop over traces. So this is still on one side, but with some crossovers. A 2-sided board has traces on the top and traces on the bottom, and vias are go between the top and bottom to connect them. You can in-house make more than that by laying up layers on top. You can make multi-layer boards that way. And then the board houses, a 4-layer board, for example, has copper on the top, copper on the bottom, and typically ground and power planes inside. And beyond that, say a computer motherboard might have 10 layers given the challenges of routing everything. So you'll typically be doing 1 or 2-layer boards in-house. Now, if you do that, you need to get the traces from the top to the bottom. And so those are vias. And so one way to make a via is, if you look at this example, this is a board and I had a via with a trace on the bottom side, but I only had one here. There was just this one place. So in this case, all I did was I made it as if I was going to make the via and mill the other side. But as a shortcut, I just simply soldered a wire to do that. And so if you just have a few crossovers, that's a fine way to do it. Something we have in the inventory is we have rivets. So these are neat parts. And what you do is you use a punch and you pop them in. And so you can use that to cleanly go between the top and bottom. In a board house, this is a commercially produced board, and the vias are plated. And so there's metal on the side of the hole that goes between the top and bottom. And so that's standard for routing it. And then for more advanced boards, there are what are called blind and buried via. So a blind via is one that goes between the top and an internal layer, and a buried via goes between 2 internal layers. Those are much more expensive. Those are for much denser boards. But these are ways you can design with more than one layer and in a prototyping process make the vias. Now, for the components we're using, if we go to Octopod, this is through hole, and we don't ever use these anymore. This is chip scale packaging, which is really tricky to solder. This is a standard surface mount. That's the most common that we use. Something we're not using that may surprise you is this is a breadboard. Breadboards are common for hobbyists. The reason we're not using breadboards is what's nice about these is they're quick and easy to experiment with, but there's a lot that's not nice. One is they need through-hole components, but we don't otherwise use those. So you need 2 complete sets of parts. Second is they have poor electrical performance. There's a lot of, for example, parasitic capacitance. Third is the joint isn't very good on the wire. So if you make a breadboard and you carry it somewhere else, it may or may not keep working. And then finally, when you're done, nothing's documented, and it can be hard to figure out what you just made. So compared to that, the process we're going to go through, in an hour, you can go from having an idea, designing a board, machining it, and soldering it. And you can do a lot of editing of the board after you made it. So the boards we've made, if you make mistakes, which you'll do, you can cut a wire, you can cut one of the traces, you can solder wires to make jumpers. You can still do a lot of prototyping, but it's with the final finished form factor, and there's a CAD workflow that's documented it. So that's why we're not using breadboards this week. So Jason, again, the reason we're not using through-hole is through-hole components, other than a few special ones for anchoring, are roughly obsolete. No new parts come out through-hole because just surface mount parts pack more densely and they're easier to produce. So legacy parts are available through-hole, not new parts. And in the labs, once you get comfortable with using surface mount, they're convenient and easy to use. If you wanted through-hole, you would need 2 complete set of parts, and better just to learn surface mount parts. So soldering, in theory, is simple. In practice, is very subtle. So for beginners this week, what's going to drive you crazy is your instructor, somebody comfortable, will come in with a soldering iron, your component, and in about 15 seconds solder it. And it's a perfect joint, it looks great. And you'll spend a whole afternoon failing to reproduce that. And so it looks easy, but it's a surprisingly subtle process. So first, what is solder? DigiKey stocks thousands of types of solder. Again, through-hole is not forbidden. And the one place where we do use through-hole, there's a question in the chat, is when you have a connector going off the board, often there's through-hole just to better anchor it. But even then, those are also becoming obsolete because, for example, in the USB connectors, I'll show you in a little bit, what they do is they have a little foot that goes into a board hole. And then they have another tab that comes down to solder, and it gets anchoring without actually needing to go through hole. And so again, through hole isn't forbidden, just we don't use it much. So there's hundreds of thousands of kinds of solder. To solder, you can use a soldering iron that heats it. In particular, there are cute little USB soldering irons. I'll add, this came up in the debugging recitation. You can get cute little USB cordless soldering irons. Then soldering stations like these let you set the temperature of the soldering iron. And then on this side is a really important tool that's increasingly important. The soldering iron solders by heating the pencil tip. This heats by heating hot air. And that's the tool we need when you do reflow, which I'll talk about in just a minute. The newest components, rather than having leads on the side, have leads underneath. And to solder with them, you need the hot air to do reflow. And so these have come way down in cost, about $100. And so I recommend having these soldering stations with both hot air and reflow. If you solder all day long, you need industrial ventilation. If you do just a little bit of soldering, the fumes from it aren't a serious hazard, they're just a nuisance. And so you can get these fume extractors, but it's not a high hazard, it's really just getting rid of a nuisance fume. Then you do need to be aware that it's surprisingly easy to not pay attention and burn yourself on a soldering iron. You can, believe it or not, just grab it from the wrong side. You just sort of reach over and you hit the tip. You can be holding it and hold apart, and you kind of slip and come in and bump yourself. And so just touching the soldering iron is a small burn. It's very, a little skin peels. It's easy to take care of, but you should be aware of you can burn yourself on a soldering iron. ROHS is a European standard to eliminate heavy metals, and so most of the world has moved through that. So solders originally had lead. Now, pretty exclusively, we just use lead-free solder. Solder is what's called a eutectic. And so there's typically at least two alloys, like copper and tin. And if you look at the percentage of them, this is the melting temperature. And at an intermediate alloy, the melting temperature is depressed. And so that's what we use for soldering. And for lead-free solder, you can get it in a wire. That's for the wire iron. You can get it in a paste. And so this is a paste you dispense, and then you use the hot air. These used to need refrigeration. Now these have been developed so they're stable at room temperature. Let's see, there's a note about a fume extractor. Oh, amusing. So the leaded we don't use anymore. In fact, I'll cross that off. And then the leaded solder is easier to use, but we don't use it anymore. The higher temperature is a little harder to use. And then there are low temp solders that we use if you have components that you need to keep at a very low temperature. But these are the solders you'll be using. So to solder with them, the very first step is you have your soldering iron, and I'll talk about reflow next. The tip of your iron should be shiny. And so over time, crud gets on the iron. And so your soldering station should have a sponge that's wet. And so you take the hot iron, you brush it on the sponge and it steams a little bit. That helps clean it. If it's really bad, you can actually get just like a wet paper towel and sort of pull it on the tip. So get the crud off. But then a key thing you do is you flow solder and you get a little layer of solder on the tip. So the whole thing looks shiny. What that's doing is that's improving the heat transfer. If you don't do that, you don't get a good joint. Then the essence of soldering, and this is where as a beginner you'll go crazy, is here's a chip, here's a lead coming down, and then here's a pad we're going to connect to. So the essence of it is this. Here comes the tip of the soldering iron in. The first thing you want to do is feed a little bit of solder. So you come in with the solder and you feed a little bit of solder. So notice right now, I've got the tip right at the junction between the lead and the trace. If I heat either one side or the other side, heat doesn't flow between them. Then this little bit of solder here, what that's doing is without it, the heat only goes through the mechanical contact. The little bit of solder spreads out the heat, so I get better heat transfer. Then what I'm going to do is just wait about 10 seconds. And so the heat is flowing up the lead, it's flowing down into the trace. Then I gently probe with the solder, And what I'm waiting for is when both sides get hot, the solder likes to go where it's hot. And so it'll nicely flow up, it'll flow down. And so I probe until it flows. And then after that, crucially, I then do nothing. I wait a few seconds more. And then I'm waiting for the solder to finish flowing. And then at the end of all of that, when I take the soldering iron away, what I see is a smooth, shiny surface. So the key phrase for this week is shiny and smooth. And when you do it wrong, what you get is something that's neither shiny nor smooth. And so a cold solder joint looks lumpy and grainy. It's not shiny, it's not smooth, it's lumpy and grainy. And these are really bad because they're not a good joint, but sometimes they're neither good nor bad, meaning they almost work, but if you bend the board, they stop working. And so you're going to see lots and lots of examples of solder joints in boards I'll show you. And if you look at the joints, what you always want to see is that they're shiny and they're smooth. Let's see. That's right, I've got this map. This is a grid of wire solder and paste solder, leaded, lead-free, and low temp. The lead-free isn't quite as shiny and quite as smooth as the leaded, but still is in the same ballpark. And then the paste you apply as a paste and do reflow, and I'm about to talk more about that. And then you get joints that look like these. And so this is what your solder joints should look like. And again, when the expert does it, it looks like that. But what's actually happening is the iron is tinned, you're gently probing, you're waiting for it to flow, you're letting it to get there, then you take it away at the right moment. It's surprisingly subtle. So we're doing manual soldering with wire solder. And so the steps are, you'll see I came in and I made a little solder bump. The reason for that is you need to hold the component down. And another beginner thing that's frustrating is sort of chasing after the component running away from you. So what I'm doing here is I'm using the solder like glue. I put some solder on a pad, then I heat that, I bring in with my tweezers. And for this week, your tweezers are your friend. They're not for changing the tires on your car, which should be obvious. But the issue is the tweezers have nice fine tips to pick up the components. And it's really sad when somebody pried with them and you find bent tweezers. So I come in with my tweezers, I heat that, and that little bit of solder there is holding the component down. It's not yet a solder joint. So now I come in here, I heat the joint, I flow the solder in, I then leave it for a moment, and then I take it away, and then here's my shiny, smooth joint. And then I make my way around to all the components, and then I come back. The very first one I use to hold it down isn't yet a real solder joint. So I reheat that and then take it away. So those are the steps of manual soldering. Drag soldering, when you have a lot of fine leads, is where you pull the solder iron back and forth. And wave soldering is where you have a tank of solder with a little wave in it and you pull the board through, and that's how it's done commercially. So one of the first things you should check is just look at your joints. If a board isn't working, look at them. The solder, in the solder itself is the alloy, and the solders we use have a flux the flux core is a material that helps clean the joint, and that's what you smell from the soldering. You can also get flux in paste or a pen, and some people swear by that just to help them with soldering. So then many of the components we're using don't have leads underneath, don't have leads on the side, but many of the chips and sensors, to save space, just have pads underneath them. And so for those, we need to do reflow. This is hot air reflow. So what I did is I dispensed with the syringe a little bit of paste on each pad. And you'll see on the trace, on the integrated circuit, I didn't try to separate it on each pad. I just made a skinny bead across them. Then I smushed the components down. And then here what I'm doing is hot air from above. And so I'm heating it. And then the hot air, it's beautiful to watch. The hot air heats up, and then the paste just sort of magically turns into solder. But now I don't need to get in from the top or side. It's soldering from underneath. And so that's hot air reflow. Then you can do it with a hot plate. This is a cute little teeny hot plate that's USB powered, that's good for boards of this size. And then you can just use like a kitchen hot plate for bigger boards. Now, a note on this is, no, the hot air, the components are designed for the hot air temperature. All of the components are spec'd for the soldering temperature, and all the ones we use are designed to withstand that. FR1 is a bad thermal conductor, and so it doesn't work to heat it from below on a hot plate. That only works for FR4 boards that are better thermal conductors. To do hot air, to do reflow with FR1, you need to do it from above with the hot air. But now, yeah, so part of the art in hot air, there's a note about flying off, is you set the temperature and you also set the airflow rate. And you don't want the airflow too fast or it'll blow everything away. You need hot air reflow with solder paste for the densest components we're using, but some people just fall in love with it. Rather than all of the feeding in wire, all of the things I described for soldering, you can just fall in love with solder paste and do everything with it. So here you just take let's go back to here. You get a syringe that you can put in the finer tip in the syringe, and then you just squirt out a little bit of paste on each one, and wave the hot air. And it can be faster to do this way and less fussy once you learn to do it. And so I recommend trying both, but increasingly we need hot air for some components, and you can use it for everything. The components are small. Depending on your eyesight, you might want to have a magnifying glass on an arm to see what you're doing. No, the hot air is very localized. So I've never gotten burned with it. You really have to work to aim it. That hasn't been a problem. And then, yeah, Jason, that's exactly right. That what's going on in this image is the copper wants to go where it's hot. And so when you heat this, this doesn't work if you put too much paste. Then you need to desolder, which I'm about to talk about. But as long as you don't put too much paste, you just heat it and it just magically gets sucked right up onto the lead. So that just after heating becomes this. Okay, so stuffing is putting components on the board. Many of the components we use are oriented. And so there's a dot or a mark. And so you need to be aware, do you put it in the right position? All of us have made a beautiful board and then realized we put the components backwards. it's not the end of the world, but you need to desolder and put it in. I showed if you have, for example, just a resistor, so the surface mount resistor has pads on both sides. The way you do it is we have two pads to connect. You make a solder bump, heat the solder bump with your tweezers, come in, holding it. Use this to hold it down, solder this side, and then come back and just clean up that joint. So we use solder to tack components down. A beginner mistake is to do the big components first. You want to stuff bottom to top, low to high, and inside to outside, center of board to the edge of the board, just so you don't block yourself. And then when you're done, there's a little bit of residue left, so you can wash the board again. Sibin is asking about dispensing the syringe solder. The I just do it. So this is the one I use, and I use this tip, and I just squeeze it out. When I need really fine, small amounts of paste that's below what I can do with the syringe, what I do is I just take a paper towel and I dispense a lump of it. And then I get something like a toothpick, and I use that to pick up a little bit and sort of paint with it is one way I do it. So then you will need to desolder. You'll make mistakes. You'll have too much solder. A solder bridge is where you have solder connecting two leads that shouldn't be. So there are many ways to desolder. Here's an example where this was intentional. This was a chip with traces that were too close together. So it was too hard to solder. So what I did here is I just made a mess. I made solder everywhere, and then I desoldered. And so to desolder, the way I do it is with something deceptively subtle. This is braid. And so the way you use solder braid is you have excess solder. Say we need to remove this solder. In theory, you come in with the braid and you heat it with the soldering iron, and the braid wicks away the solder. But here's the trick. If you just hold the braid against your joint with the soldering iron, nothing happens. You need to prime the pump. You need to flow a little bit of, you need to add solder to remove it. You add a little bit of solder. The little bit of solder goes into the braid and helps the braid heat up, and then the braid wicks it away. And so as long as you have the trick of adding solder to the braid to remove it, then this is what I prefer to use. You can get desoldering tweezers. You can get a vacuum tweezer, a vacuum soldering iron that sucks away the solder. You can desolder with hot air. One of the ways I desolder is if I have a whole chip that's wrong, I take my board, I have this chip that I want to remove. I hold the board with my tweezers with one hand. I come in with the hot air gun with my other one, and then I just hold it above the table a few inches, and I just wait. And the hot air gun heats all of this, it softens the solder, and then after a minute or so, just the board drops away and you're left holding the component you didn't want. And so you can learn to do that easily. So that's desoldering. Then you can do a great deal of editing. If you look at a PCB wire jumper, if you look in a commercial product, you'll see stuff that looks like this. Somebody designed a PCB and they made some mistakes. And so you cut some traces and you put wire jumpers in for other ones. And you'll see commercial products that have these because they want to ship some before they make the next board. So you can do a great deal of editing, cutting traces and adding traces. Then for short run production, the most well-equipped labs have pick and places that automate, but you need to make about 100 boards before it's worth the effort to set them up. And then if your board is going to go in a tough environmental condition, when you're done, you can make an epoxy or silicone coat to seal your board. Now, you need to send the design to a machine. So board houses universally use Gerber. And so the CAM work, your PCB process will be able to produce Gerber. That's what you send to a board house. There's a comment about, there've been a number of open source pick and place machines. I've never seen one really successful. Interesting, I haven't seen this one. Svavar is noting this one actually works. Interesting. So Gerber is what board houses use. In-house, we use PNGs, not JPEGs. Remember, I wanted JPEGs for compression. PNGs don't compress. But in this case, we don't want any compression. We want it to be pixel perfect. PNGs are a more recent format, and they're convenient because they're easily edited. So we use PNGs in-house, but board houses use Gerbers. So you need to convert your design to something to send. And so one of the main reasons I wrote mods originally is for this process. And this is an earlier version of mods. Kyle Pierre's noting about 2 of those pick and places. Interesting. Good to know about that. So what I'm doing is I'm reading the board in. Mods figures out the path for the cutting tool to cut it, then can send it off to the machine. And then we can do a second job where we bring in the outline of the board. And then this does multiple passes to cut the outline. Plus the board doesn't need to be square. It can have holes. It can be an interesting shape. And that makes the toolpath to cut it out. Then here is a test pattern. This is stepping internal and external steps in thousandths of an inch. And so here I've made it with the 1/64 inch end mill. And so when the gap gets smaller than that, it can't get in. And you'll see it's getting down to about 10 thousandths of an inch before it starts pulling up the trace. So this is what it should look like. The machining process, unlike the vinyl cutting, is completely consistent. It should always look like this. Here I've redone it with a 10 thousandths of an inch. And so you'll see I can get down to a finer gap here, and I can get down to a finer trace there. We use that, but you can see the tip is so tiny. The annoying thing this week is breaking end mills. It's not hazardous to you. It's hazardous to the health of your lab because it's money and you need to keep buying end mills. As long as you're machining properly, you should never break an end mill. The ways you break end mills tend to be if you set the 0 wrong, if it's too low, it's one way. One is if the board isn't properly mounted, so it's flexing. Another is if it's not properly anchored, so it's slopping around. Those are all ways to break end mills. And that should never happen if everything's working properly. Then this is using a fiber laser. And you see with the fiber laser, I can get even finer still, but it's a much more expensive tool. So as a group, I want you to just go through characterizing your PCB process, which can be just making these test patterns and confirming everything looks right. If it doesn't look right, standard thing to do is just take everything apart in your machine, clean it, put it all together again. And then something you could do, not individually, but as a group, is I want you to each know how to make boards, but you could pick one design and send out to one of these board houses just to go through the process of using a board house. Then main job this week is to take the board you designed. I want you to make it, and crucially for this week, I want you to test it. And that's where the recitation comes in, that it's with high probability what you made won't work. And so that is the domain of debugging, of figuring out all out of the many reasons why it didn't work. So I want you to make it and test it. And then the extra credit thing is try other processes. So begin by machining, because I want everybody to learn that. You can try vinyl cutting. If you have the fiber laser, use the fiber laser. If you plan carefully, you can use friendly etching materials to do etching, but experiment with other ones. And the goal is, now, when I say the development board you designed, this can be the board you did in the design week, but it's also okay if you want to update the design and make a new design based on progress on, for example, thinking about the final project. Okay, so in theory, this week is straightforward. You just send a job to the machine and solder the components. In practice, if it's done wrong and you get a beautiful looking board, if things go wrong in the board fab, the board looks ugly. If it goes wrong in the machining, you break an end mill and your instructor is unhappy. And the soldering that looks easy and fun, you can spend an afternoon failing to get a good solder joint. And so it is sort of Zen-like. You need to be at one with the joint. You need to sort of feel the solder joint. You need to sort of feel what it feels to tune into it. To get a nice solder joint. And then once you learn that, it's a quick, easy process, but you need to be aware it's not just heat solder, but you need to actually pay attention to how the heat is flowing through the joint. Okay, so at the end of this week, you should have a working board, and then you need to be ready, because after this, we're going to then go through input devices, output devices, networking, and you're going to be making lots of circuit boards based on what we covered this week. So no recitation next week. And as always, thanks to the three amigos, the Saturday open time, for help with everything. If in doubt, there was a note in the chat, the room temperature lead-free paste with the hot air station, it's at least as easy to learn to solder with that as with wire solder, and lets you handle many more types of components, and can be really quick, because instead of doing each joint separately, you just dispense the solder. And so do spend time with the paste. That's growing in importance. Okay, happy electronics production, and see you all in a week. Let's see, Jason's asking about solder wire. Yeah, Jason, in each week, the top link goes to the almost migrated inventory. And so I've got links in here to the solder that I recommend. Okay, bye-bye, everyone.
Adiós.
Bye.
Adiós.
Adiós. Chao.